Okay, so since today became a technological mess, we want to go through today's lesson again on a video so that you can watch this and really make sure that you didn't miss anything from lesson 6.0. So the warm-up, I think we got through okay. I'm just going to actually go to the answer key to the warm-up question so we can just talk our way through it. So you were given two functions, f of x and g of x. F of x was a linear function equal to 2x. G of x was a quadratic function equal to x squared. And we were using this mapping diagram to really stress a difference between these two functions. In function f, we can see that every input has its own unique output. And we can see that every output came from a unique input. So there's no repeating x values, no repeating y values. When we look at function g, we can see that yes, every input has its own output. However, that output of 4 is being repeated with 2 inputs. So this is a special type of function for f. They're both functions, but what we do is we define f as a one-to-one function. And that's what we call a function where every element in its range corresponds to exactly one element in the domain. So to be a function, you don't repeat x values. To be a one-to-one function, you don't have repeating y values. So then we worked on question 1. And again, I think this one was okay before the glitching started. So I'm just going to talk off the answer key, and then we'll do a few other ones in real time. So for exercise 1, we asked you to look at 4 tables and to pick out which one would be a one-to-one function. Now, in order to be a one-to-one function, you have to be looking at a function itself. So choice 1 and 4 were actually not functions to begin with because they had repeating x values. So when we get rid of those two choices and we look at our two functions, choice 2 and 3 are both functions. Choice 2 has a repeating y value. If you see there, -2 goes to 1 and so does 0. So only choice 3 would be considered a one-to-one function. None of my x values repeat and none of my y values repeat. So then we got on to number 2, and I think this is when things started to get a bit messy with the internet. So let's look at this one again. So we were giving you 4 graphs, and we asked you to circle the 2 graphs that were functions. So now when we're looking at a graph and we want to determine if something is a function, we're going to use the vertical line test. So if I look at function 1, or I look at, graph 1, I kind of gave the answer away there, I can see that this is a function because it passes the vertical line test, meaning each of these vertical lines only comes in contact with my graph at one point. If I look at graph 2, it does not pass the vertical line test because I just drew one vertical line and I crossed this graph 4 times. So that would not be a function. 3, also same thing, a circle is not a function. Choice 4, yes, that is a function. So when it says explain how you know they are functions, we'll say graphs 1 and 4 are functions because they pass the vertical line test. Total acceptable answer for something when you're looking at a graph and you want to determine if it is or is not a function. Now, if you also wrote graphs 1 and 4 because there are no repeating x values, every x has its own unique y, you could also use the definition of the function here, but using the vertical line test is a completely correct way to describe why we're choosing those two as our functions. Now, of the 2 that we circled, now we're being asked to determine which of these would be one-to-one. So what I'm just going to do here is I'm going to erase my vertical lines and kind of go over this a little bit different. So in order to be one-to-one, we need to not have y values repeat. So what I'm going to do here is I'm going to use a different color. Let's just think about maybe estimating a couple points on this graph. So on this line, let's say maybe this is, I don't know, some negative x values, maybe like -2, -1, maybe this point, again, I'm making these up, -1, 1, right? And then maybe this is, I don't know, 1, 3. Again, this might not even make a line, so I'm just using these numbers to show you that out of the points I'm picking, there's no repeating x's, there's no repeating y's. If I look at graph 1, let's just say I pick these 2 points. And I'm trying to stress that they look like they're almost on the same y value, right? So maybe this is 1, 2, and this is, I don't know, negative 3 comma 2. These would share the same y value, and that would be true for any 2 points I picked if they lie on the same constant line for y, meaning this horizontal line. Any horizontal line here is going to come in contact with this graph twice, and that would be 2 points that would have the same y value. So there's actually a test, just like the vertical line test lets us know if a graph is a function or not. The horizontal line test allows us to determine if a function then is what we call one-to-one. So let's say, I'm just going to get rid of the points because I made them up and they're not accurate, but let's say I drew a bunch of horizontal lines now through graph 1 and 4. Graph 1 does not pass the horizontal line test because that horizontal line is coming in contact with the graph more than once, whereas graph 4 does pass the horizontal line test. So we can say here, graph 4 is 1-to-1, because it passes the horizontal line test. So the horizontal line test is only a test you would perform if a graph already passed the vertical line test. So if it passes the vertical line test, it is a function. If it passes the horizontal line test, it is now what we call a one-to-one function. You could also, again, have used the definition there and said there are no repeating y values, or every y comes from a unique x, but the horizontal line test, just like the vertical, is just a little bit easier to describe that. So right below that in your notes, if any given horizontal line passes through the graph of a function at most one time, then that function is 1-to-1. So we're just now writing it down, what we just discovered above. This test works because horizontal lines represent constant y values. Hence, if a horizontal line intersects a graph more than once, that y value or that output has been repeated, meaning it fails the horizontal line test. It is not 1-to-1. Okay, let's keep going. So we split this lesson up into, first let's talk about what makes a function 1-to-1, and then let's talk about what an inverse is. And then we're going to kind of show how they relate. So an inverse, we're just going to start out by telling you that you can find an inverse just by switching x and y. So what we wanted to do here was just start out by, okay, here's a table from a function. Let's switch where x and y are, and let's look at that new graph that we create. And what we actually create just by switching x and y, that is the inverse. So I know that if this is my original function f of x, this is the inverse, that was supposed to be an arrow, inverse of f of x, just by switching x and y. So I'm just going to save us a minute. I'm going to go down here, and then we'll keep going over that. So if I graphed those 5 points, I'm going to get a graph that looks like this kind of sideways parabola. And that is the inverse graph to the quadratic y equals x squared. Now, if we look at this inverse graph, though, we might notice something. It is not a function, right? Because this would not pass the vertical line test. So it is what we call an inverse, but it's not an inverse function. It's just an inverse. Or maybe won't even use that word inverse here. This is not a function, but it is the inverse of f of x. Now let's go back to the second question there. The linear function is shown graph below. On the same set of axes, draw a graph of this function's inverse. So now I don't have a table, but I could make one because they gave me nice points here for f of x. So I'm just going to kind of list them in a table. So this first point, negative 1, 2, 3, 4, 5. This is negative 6, comma 1, 2. All right, so this grid is going 6 up, 6 down. Okay, so this first point is negative 6, comma negative 6. Then we have negative 3, comma negative 4. Then we have 0, negative 2, 3, comma 0, and 6, comma 2. So I was just picking the point values of those 5 ordered pairs that they graphed on my function. And now what I'm going to do, I'll use a different color, is I'm going to talk about its inverse. I'm just going to call it y for right now. So I'm going to switch all of these ordered pairs around. So instead of, well, -6 would be the same. -3, -4 is going to become -4, -3. 0, -2 will become -2, 0. 3, 0 will become 0, 3. And 6, 2 will become 2, 6. And I'm going to plot that. So the first point's the same. Then I have -4, -3. -2, 0. 0, 3. And 2, 6. I'm just going to try to make a straight line there using my line tool. Hopefully I can. Yes. And this is the inverse of f of x. Now, something you might see here is that this graph is a function. So even though in question number 1 we were given a function x squared, we found its inverse, the inverse was not a function. In this example, this inverse would pass the vertical line test. So this is a function. So before we kind of bring the whole idea of one-to-one and inverse together, let's just add one more thing on to inverse. If my inverse of my original function is also a function, there's a notation we use. It's function notation, and we add in this little, it almost looks like an exponent, but it's not. It's just a notation with this -1 to indicate that this is the inverse of f of x. So instead of having to write inverse of f of x, it's much easier to just use this notation that represents that. So f inverse of x, as opposed to the original function, which is just f of x. Now, if you look at the two functions, I'm going to go down here because I have them both graphed on this page. What's interesting is this is similar to the first warm-up where we looked at a quadratic and we looked at a line and we did the mapping diagram. And we said the quadratic was not one-to-one because there was a repeating of y's, and the linear was one-to-one because the y's did not repeat. Now, if you look, the linear function, number 2, has an inverse that is a function. The original function in number 1, which was the quadratic, has an inverse, but it's not a function. So the connection we want to make here is this original quadratic, this was not one-to-one, right? We have repeating. It doesn't pass the horizontal line test. This quadratic, I could draw a bunch of horizontal lines. They're all going to cross twice. Whereas the linear function is one-to-one. The one-to-one function's inverse is a function. The quadratic, not one-to-one function's inverse is not a function. So this connection here is you can actually tell based on an original function whether or not its inverse will be a function. So if the original function is one-to-one, the inverse will also be a function. So if the original function passes the horizontal line test, like the linear does, then the inverse will pass the vertical line test. If the original function does not pass the horizontal line test, then its inverse will not pass the vertical line test. It's just a connection we want you to make. It's going to be something important when we look at, other examples of inverses. And it's a nice thing to know before you even calculate the inverse, if the inverse will be a function or not. So if you look at example 1, I know we didn't even get to do this one in class, but now we have time. What I want you to do is state the domain and range of that function, and then graph the inverse based on the points plotted. You're going to switch x and y, graph it, and then state the domain and range of the inverse. And what I'm going to need you to do right now is actually pause the video, and then I'm going to go over this. So pause the video, try this question, and then we'll go over it. Okay, so hopefully at this point you've tried this. If you stated the domain and range of the original function, which is, I'm just going to highlight the original one in orange, you would get that it started at a domain of -7. I can see that here. And it went all the way to a domain value of +7. So that would be the domain. You could write it like this. -7 less than or equal to x to +7, or you could use interval notation and use the brackets. Now, for the range, we can see it starts down here at a y value of -5, and it goes up until this +5 y value. So range, you look from the bottom to the top of the graph. So -5 to 5, just don't forget to change range notation to have a y instead of an x, or you could use interval and just bracket -5 to 5 bracket. Now, when we want to graph the inverse, what I did was I looked at these points and I said, okay, -7, -5, that's going to become -5, -7 on my inverse. The point 1, 3 is going to become 3, 1, which would be here. And then the point 7, 5 would become 5, 7. And also, I guess this was a nice looking y-intercept here. So I was able to plot that other nice point. So we had an x-intercept here on the original function of -2, 0. So then we put a y-intercept here of 0, -2. So if there were any other nice points you saw, you could absolutely have indicated them. But just taking the 3 points you were given and plotting them opposite x and y values would produce this inverse graph. Now, if you looked at the inverses graph and stated its domain, it's going from -5 to +5. And if you look at the range, it's actually starting down a little lower, -7 up to +7. So what you should notice here is that the domain and range of the inverse actually came from the original function's opposite place. So the domain of the original function became the range of the inverse, and the range of the original function became the domain of the inverse. And the reason this makes sense, domain is made up of x values, range is made up of y's, and when we find an inverse, we switch x and y, which means our domain and range actually switch as well. So the domain of an original function becomes the range of its inverse. The range of the original function becomes the domain of the inverse. And a nice way to kind of look at this is this picture down here. So if this is the domain, here's my original function, here's my domain of f, here's my range of f. Now for my inverse function, which again, if you even notice here, they switched the input and the output, right? So it was f of a equals b, now it's g of b equals a. That now has the range coming from the domain of f, and the domain of g comes from the range of f. So this is just a visual representation of how those two things will switch. Okay, so now let's go and try 2 questions and actually calculate the inverse by hand. So it's one thing to have a set of, ordered pairs, or to have a graph where you can look at points. If you're just given the function and you want to find the inverse equation, you're still going to switch x and y. So that's still the main way that we find an inverse, is to switch x and y, with a few added things to think about. So if your original function is in f of x notation, you're going to want to get rid of that and just start with y. Because if you don't see a y, then it's hard to switch x and y. So now that I know f of x is really y, I'm going to switch where x and y are in the equation. And now what I want, technically this is my inverses equation, but we don't ever use equations in x equals form. We can't type them into our calculator. We can't look at them and recognize the type of function they are. We want to see y by itself. So once you switch x and y, you're going to now solve for your new y. So I'm going to subtract 5. I get x minus 5 equals 3y. I'm going to divide by 3, and I get y is equal to, now I'm going to probably just separate this and make it 1/3 x minus 5/3, just because my original function was in slope-intercept form. I'm going to make my inverse also in slope-intercept form. Now, my original function was f of x. It was a line. We know that lines are 1 to 1, so we know that this equation represents a function as well. I'm going to use function notation. F inverse of x equals 1/3 x minus 5/3. And that will be my inverse. So if you plugged the original function into your calculator, if you plugged the inverse into your calculator, you would see two graphs, or really if you went into the table of values, you would see values that are switched. So all the x and y's from the original function switch places to give you the x and y's of this inverse function. And then we're going to try one more. Now this one, it's the same process, although because the function is this rational function here, it just becomes a little bit more complicated in solving for y, but same start. So I'm just going to change this to y equals, and then I'm going to start finding my inverse. So I'm going to switch x and y. And now I need to solve for y, but y is in a fraction, and it's also in two different terms. So I'm going to start by cross multiplying, and I'm going to get x times y is xy, y plus 1 times 1 is y plus 1. And now, because I need to actually get y alone, I can't have it in two different places in my equation. So what I'm going to do is I'm going to get y to the same side of my equation. So xy minus y equals 1. And now I have to kind of be a little creative here. I want to get y alone. It's in two terms, but it's in these two terms, meaning it's a common factor in xy and in y. So I'm going to use GCF factoring to factor it out. The benefit of that is that now I have y in one factor by itself. So because it's connected right now to this x minus 1 factor through multiplication, I can divide that away. And now I get y is equal to 1 over x minus 1. Or I can go back to my function notation for the inverse. F inverse of x is equal to 1 over x minus 1. I hope this video was able to, close some holes from today's lesson since so many of us were logged in and logged out. Please make sure you went through your notes packet, watch this again, fill in your notes where you missed things from class today, and take a look at the practice and the homework so that, you're able to go through a few of these on your own before coming into class tomorrow. I hope this was helpful, guys. We'll talk to you later.